Hello everybody. Today we are going to cover some topics in MG University BSc Electronics paper Network Theory. The topics are stability of an electric network and Routh-Hurwitz criterion. So what do you mean by stability of an electrical network? It refers to the ability of the system to perform satisfactorily. When the system is excited by a bounded input and if the output is bounded, then the system is said to be stable. What is meant by a bounded signal? Bounded signal means its maxima and minima should have finite value. And that means if you give a bounded input, if the output is having finite value, then the system is said to be stable. For a bounded input, if the output is unbounded, then the network is unstable. That's the definition of stability in the time domain. The ratio of response to excitation gives the transfer function of the network. And if we take the Laplace transform, we get the transfer function in S domain. That is the complex frequency sigma S equal to sigma plus j omega. The transfer function in S domain can be represented as T of S equal to P of S divided by Q of S. And equating the denominator polynomial equal to 0, we get the characteristic equation. And the roots of this characteristic equation gives the location of poles in S-plane. This location of these poles is very important. The roots of this characteristic equation are called poles, and the location of this pole in the S-plane determines the stability of an electrical network. This is the complex plane shown here, the imaginary axis or j omega axis, real axis or the sigma axis. And if the location of pole is in the left half of the imaginary axis, then the electrical network is stable. If the location of poles are in the right half of the imaginary axis, then the system is unstable. So the definition of stability are, if all the poles lies on the left half of S-plane, then the system is said to be a stable system. And if non-repeated poles of the system lies on the imaginary axis of the S-plane, then the system is said to be marginally stable. There can be some poles on the imaginary axis that they should not be repeated. If they are non-repeatable roots, and then the system is said to be marginally stable. That means the output of the network will be oscillatory in nature. If at least one pole of the system lie on the right half of the S-plane, then the system is said to be an unstable system. Consider a network with a characteristic polynomial Q of S equal to B0 S raised to M plus B1 S raised to M minus 1 plus B2 S raised to M minus 2, etc. up to Bm. So if the order of this characteristic equation or characteristic polynomial is large, then it is difficult to solve this equation and get the roots. That means it's difficult to get the poles or location of poles to check the stability of the system. In order, Routh-Hurwitz criterion help us to find the stability of such network without solving the characteristic equation. Necessary condition for stability are, consider this characteristic equation. All the coefficients of the characteristic equation should have the same sign. That means B0, B1, B2, etc. up to Bm. All these coefficients should have same sign, and there should not be any missing term. Those are the necessary conditions for stability. If the above given conditions are not satisfied, then the network is said to be unstable. The statement of Routh-Hurwitz criterion is, Routh-Hurwitz criterion states that any system can be stable if and only if all the coefficients of the first column of the root array have the same sign. You will see what is root array is. If there is a sign change, then the number of sign changes in the first column is equal to the number of roots of the characteristic equation in the right half of the S-plane. That is equal to the number of roots of with the positive real parts. The procedure of Routh-Hurwitz stability analysis is consider the following characteristic equation: Q of s equal to B0 s raised to m plus B1 s raised to m minus 1 plus B2 s raised to m minus 2 plus etc. up to Bm. When the coefficients B0, B1, etc. up to Bm are all of the same sign and none is 0, we can form the first two rows of the root array as from the characteristic equation as take B0, B2, B4, etc. in one row, then B1, B3, B5, etc. in another row. That forms first two rows of the root array. Okay, if the order of the characteristic equation is m equal to 5, then we can write s raised to 5, s raised to 4, s raised to 3 up to etc. s raised to 0, and then we write the first two rows from the characteristic equation. Then we have to calculate the remaining terms in the root array. They are calculated as follows. C1 is calculated from the previous two rows. That is this from this row and this row. So C1 is the determinant of these four terms. Negative determinant of these four terms divided by B1. That is B1, B2 minus B0, B3 divided by B1 is called C1. What is C2? C2 is calculated from this column and this column. B1, B4 minus B0, B5 divided by B1 is C2. So then we have to calculate D1. D1 is C1, B3 minus B1, C2 divided by C1. So what is D2? D2 is from this row and this row, calculated from these two rows. So C1, B5 minus this is 0 divided by C1 is D2. Other becomes zeros, other terms become 0. What is E1? E1 is calculated from this row and this column and this column previous from of the previous two rows. So it is D1 C2 minus C1 D2 divided by D1. What is F1? F1 is E1 D2 minus 0 divided by E1. So we get all the coefficients of the root array and we complete the root array as this. So that procedure is described here. What is C1? C1 is B1 B2 minus B0 B3 divided by B1. C1 is B1 B2 minus B0 B3 divided by B1. That's written here. So all these coefficient definition or the procedure of finding those coefficients is shown here. You can go through this equation. According to Routh-Hurwitz theorem, the number of changes in the sign of the first column to the right of the vertical line in the array from top to bottom is equal to the number of roots of Q of s with the positive real parts. So once we get the root array, we travel from the top to bottom of the first column of this coefficient matrix of the root array. And if there is a sign change, then the system is unstable. If there is no sign change, then the network is stable. To get a stable system, the roots or poles must have negative real parts. And if there is a sign change, means number of sign change is equal to number of roots with the positive real parts. That means number of poles in the right half of the S-plane. So if there is no sign change, all poles will be in the left half and the system is stable. According to Routh-Hurwitz criterion, the system is stable if and only if there are no changes in the signs of the first column of the array. This requirement is both the necessary and sufficient condition for stability. Now you know what is the necessary condition and sufficient condition for stability of an electrical network. Now we will do an example problem. Okay, the question is, check the stability of the system whose characteristic equation is given by s raised to 4 plus 2 s cube plus 6 s square plus 4s plus 1 equal to 0. Since the order is 4, we complete the root array by writing first s raised to 4, s raised to 3, s raised to 2 up to etc. s raised to 0. That means for m equal to 4, we will have m plus 1 rows for the root array. Then we write first two rows of the root array from the characteristic equation. So the coefficient of s raised to 4, s raised to 2, and this one comes here. Okay, then the coefficient of s raised to 3 and s raised to 1, and next term is not present. So there we will put a 0. Then we calculate the remaining coefficient from this. So what is this one? This is 2 into 6 minus 1 into 4 divided by 2 equal to 4. And what is this one? This 2 into 1 minus 1 into 0 means 0 divided by 2. That is 1. What is this term? This term will be 4 into 4 minus 2 into 1 divided by 4. That is 3.5. What is this term? This will be 3.5 into 1 minus 4 into 0 is 0 divided by 3.5. That is equal to 1. Once we complete the root array, we travel from top to bottom of the first column of the root array. So if we travel from top to bottom, there are no sign changes. That means there are no roots with positive real parts. That means there are no poles in the right half of the S-plane. That means the system is stable. The advantages of Routh-Hurwitz criterion are we can find the stability of the system without solving the equation. Here we are not solving the characteristic equation. Without solving the characteristic equation, we can find the stability of the network. We can easily determine the relative stability of the system. By this method, we can determine the range of K for stability in the case of an active network having controlled sources. If our network is an active network with a control source, and we can determine the control variable, the range of control variable for which the system is stable. By this method, we can also determine the point of intersection for root locus with an imaginary axis. So what are the limitations of Routh-Hurwitz criterion? This criterion is applicable only for a linear system. That's one limitation of Routh-Hurwitz criterion. If the system is linear, then we can apply Routh-Hurwitz criterion. It does not provide the exact location of poles on the right and left half of the S-plane. In the case of Routh-Hurwitz criterion, we are not solving the characteristic equation, so we don't know the exact location of poles in the S-plane. In case of characteristic equation, it is valid only for real coefficient. Okay, if the characteristic equation have non-real coefficient, then we cannot apply Routh-Hurwitz criterion. Those are the limitations of Routh-Hurwitz criterion. That's all for today. I hope you all understand what is covered here. If you have any queries, please contact me. My contact details are shown here. Thank you all. Have a nice day.